Hi, this is Mr. Sapone, and today we're going to look at vectors. We're going to introduce vectors. Thus far in physics, we've been using the kinematic equations a lot. We've studied motion, and we've really been concerned with motion in one direction. We may have had an airplane accelerating on a runway in the x direction, and we talked about free falls. Free fall and objects being thrown up and objects being dropped. And we've really been looking at motion isolated. But in the real world, motion is going to occur in a combination of directions. Motion is not going to be restricted just to the x direction and or just to the y. Think about when you throw a baseball. The baseball is going forward, but it's also coming up and down, and any projectile really. So what we want to do is we want to look at vectors to help us understand projectile motion. So we're going to introduce vectors here. And imagine trying to swim directly across a river that has a current flowing in a direction perpendicular to your motion. So you're trying to swim across the river from this point to this point, and the river is flowing in that direction. So you're not going to be able to swim directly across because the current's going to pull you down some. So if you wanted to get directly across the river, you would actually have to swim upstream a little bit. That way, as you swim a little bit this way, the current brings you down, you would reach your destination. And of course, depending on your speed, the rate at which you can swim, and the rate of the current will determine whether this is actually possible or not. So most of the time we have to deal with motion in two dimensions. Water problems, anytime we have projectiles, rockets being launched, baseballs, golf balls, all sorts of projectiles. So we're going to deal with a lot of motion in two dimensions. And really simply, if you push a box in that direction, the box is going to obviously move in that direction. That's pretty commonsensical, to invent a word. And if you were to tie a string to a box and you were to lift it, the box would obviously go up in the air. And I'm using arrows to denote the direction of the applied force. And what we're going to see is that we're going to use arrows to represent vectors in physics. And if you had a box that you were to simultaneously push and pull upward, that box would actually go in that direction, this direction right here. So the box is going to be moving this way, and simultaneously it's going to be moving up. So it's going to appear to be going off in this direction. And that's essentially what we're going to use vectors for. This is a vector, this is a vector, an applied force, and when you put these two vectors together, you end up with this one right here. So that's kind of what we're getting into when we're talking about vectors. And the red arrows represent component vectors. These red arrows are going to be component vectors. And when you add these two vectors together, they're going to equal a resultant vector. So this vector plus this vector is going to equal this vector. So these are component vectors. And the cool thing about vectors is they have both magnitude and direction. That's the main thing. The magnitude is 50 newtons. That tells you how strong the vector is, and the direction it's pointing in tells you the direction of the applied force. It's up. And in this case, it's over. Now, I didn't put in a magnitude here, but you could simply calculate it using trigonometry, and we're going to see how to do that in detail. So for now, we have component vectors and resultant vectors. The resultant is just a combination of two other vectors. So we add these two vectors together, and they show us the resultant, or the net direction of the force. And the idea between vectors and scalars, there are scalars and vectors. A scalar is a quantity with magnitude only. Things like time, mass, volume, and length or distance. Generally, if you give a time, you don't give a direction with it. It only has an amount, 10 seconds. You don't say 10 seconds to the west or something like that. Or you don't give a volume of 5 centimeters cubed eastward. That really makes no sense. A vector is going to be completely different. A vector is going to have both magnitude and direction. That's why when we're dealing with free fall, gravity down was negative 10 meters per second squared. We called going down negative, and that meant all motion upward was positive. Same thing with x direction of motion. When we were going to the right, we called that motion positive. When we were going to the left, we called it negative. And we had to do that because we were dealing with vectors, and you have to consider direction when you're dealing with a vector. Vectors have both magnitude and direction. Scalars only have magnitude. So, and you might know this little guy. He's Vector from Despicable Me. He is a criminal that commits crimes with both direction and magnitude. And just to show a concrete example of the difference between a scalar and a vector, we're going to answer this question. A person briskly walks across a 10-meter room and halfway back in 5 seconds. So we're going to calculate their average speed and average velocity. So this room is 10 meters long, going this way. So the person is going to start here, walk all the way across, and then halfway back in 5 seconds. So we want to calculate speed and velocity. So the person goes all the way across, 10 meters, and then halfway back, and they end up right here. So how do we calculate speed? Well, speed is simply the distance traveled divided by the time it takes to travel that distance. How far did they travel? Well, they went 10 meters across and 5 more meters back. So they went a total of 15 meters. Your total distance traveled is 15 meters. You did that in 5 seconds. 15 over 5 is 3 meters a second. And that's relatively straightforward. Now the question is, what is their velocity? And velocity is not distance divided by time. It's something called displacement. And displacement is a vector. Direction is important. And what we're going to see is displacement is not how far you traveled, but how far you are from where you started. Displacement is you started here, you ended up here. How far away are you from your initial position? Your displacement is your change in position. And hopefully you know that you went to 10 and halfway back. So this should be 5 meters. So your displacement in this case is only 5 meters, and it took you 5 seconds to have that displacement. So your average velocity, your v bar, and this is your average speed, your average velocity is 1 meter per second. And the important part to consider here is that speed is most definitely a scalar. Speed does not care about direction. Velocity is a vector. Velocity uses displacement. Displacement is also a vector quantity, whereas distance, which is using speed, is a scalar. Displacement does not equal distance. So when you're using speed, equals d over t, and velocity equals x over t. An x and a d are completely different. One is distance, one is displacement. Displacement is how far you are from your initial position. And that could be a positive value or a negative value, depending on whether you are going in this direction or the opposite direction. So hopefully you have some understanding of vectors and scalars and why we need them. Motion generally occurs in more than one dimension. But before we studied motion in 2 dimensions, we of course needed to learn how to do motion in 1 dimension. But vectors have magnitude and direction. Scalars only have magnitude. This is Mr. Sapone.